Okay. I'm afraid I've been having some technical difficulties, so there's no comedy song this morning. However, I may patch something together for the recorded version. We'll see. I guess we'll just dive straight into it. You should have seen an assessment pop up on your Blackboard. Obviously, there'll be a new assessment today, and that will be based on the stuff that we will do today. We've kind of caught up with that. Okay, if there's no other questions, or any questions at all, when I'm talking, I do feel that I'm going slightly madder than normal and just talking to the computer. So do let me know if there's anything that you want me to go over a few times here. So let's switch over to the thingy. And what we'll be doing is more on curve fitting. So last week, right at the beginning, we did a sort of introduction to polynomial fitting, and we did it in a slightly ad hoc way. What we did was define this square error, essentially the vertical distances between the predicted line and each of the actual measured data points, and we worked out a way of minimizing that distance by taking partial derivatives with respect to the parameters of our model. And I got in the assessment that handed in by 3 o'clock today, by the way. I wanted you to sort of derive that by hand. But what I'll do in this lecture, hopefully, is provide a half a way towards. I'll provide a mechanism for doing that more systematically from a fit. And then, if there's time, but probably I'll do it in a separate video on Friday, I'll sort of derive it explicitly up on the board. Okay, so curve fitting 2, and essentially the idea is to carry on with what we did before, but instead of limiting ourselves to some polynomials, in this case you've done linear, so just an intercept and a gradient, or adding in the square of the independent variable or the cube of the independent variable in varying amounts that depend on a single parameter in a linear fashion. What we'll do is try and extend it so that we can take any type of basis function. So replace that x squared, x cubed with sine of the variable, or exponential functions, Gaussians of the variable, and see how to do that. And we'll try and come up with a more systematic way, which might make coding it up a little bit easier as well. Probably should have got the fancy pointery thing. That would have been quite useful. I'll have to make do. Right. So let's think about how we can define our model a little bit more in a slightly more general sense than we've done up to now. So let's say that yi, which again will be the ith measurement, so we measure an actual signal yi, position here, and we've also measured its position on the independent variable. We've got the independent variable value, and we've got this dependent variable value there. So this actual value of it that we measure may be influenced by various things. So we could be off because our model is too simple, or we could be off because the measurement contains some noise from some sort. But anyway, we're going to fix our model up in front before we do anything, at least its form, and then we're going to work out some parameters that give us the best model of that form in the sense of minimizing these squares of distances between our model and the actual data. So the general way I'm going to write it out is like this, that the ith observed measurement is going to be equal to a first parameter, so this is some number that we're going to determine, times some function that only depends on the position along the independent axis. So in our linear model, our first function here was just a 1, or the independent value to the power of 0. So no matter where we were along the axis, we added in a 0. Then we had a second function, and for the linear model, we had a1, a parameter we determined, and then z1, so some function of x, and in this case, it was just x itself. And we stopped at that point for the linear model, and then we said there could be some amount of noise at that data point. As I say, that can be genuine noise, or it can be that our model isn't capturing the underlying processes that are going on. And I'll refer to these things, these z, that depend on the independent variable as basis functions. And in general, we're going to have n data points and m basis functions. So instead of having the linear or the quadratic or the cubic polynomials that we've had a little bit of a look at, we could, for instance, have a model like this. I've missed out the error term here, that the y is equal to some constant offset, some a0, times a basis function that's just 1. And then we could have the cosine of the distance, and we could scale it by some parameter. But we're not going to optimize that parameter, because optimizing that parameter would be non-linear. It would be a non-linear problem. But the value depends only linearly on this parameter here, this a1, which is what we're going to optimize. We'd have to pick this omega up front, so we could ignore that for now. So the cosine of this and the sine of this, that will give us one model. How will we go about actually taking a bunch of data and then deciding what the best values of a0, a1 and a2, or in general a up to a0 up to a minus 1 are going to be? So let's write this out in matrix notation, our set of equations. So we've got the observed dependent variable value, the observed value of y. I'm just writing out again what we had. It's going to be our first parameter, a0, which we're going to determine, times the first basis function evaluated at the value of the independent variable. Then the same, but with a second parameter and the second basis function. And then so on. And then there's an error term at the end for each one. So if you like, this should be an m minus 1 actually in the thing. So we do this sum, and I can write this out in a matrix notation vector form later on. So it's the sum from 0 to m minus 1. This is the j, so the ith value is the sum of these things here. So the error's there. So the j is labeling the different parameters, and the same for the second parameter of this z. So this z is going to be a matrix, and this a is going to be a vector. So in general, we've got y. So the y contains my sort of list of the different measured values at different x values. The A is a smaller matrix in general that contains the parameters of the model. Our A's, so A0, A1, A2, A3. And then the Z, if I look at what I've got here, it's going to be like this. So it's going to be a matrix that contains the first basis function evaluated at the first position, then going across the column, all the first row, sorry, going across the columns, all the first row are going to be evaluated at the position of the first independent, the independent variable of the first measurement, and they're going to be, we evaluate the different basis functions at that point, and then we do the same there. And so if we've got ZA, we multiply this out, we'll get Z0, A0, Z1, A1, evaluated at the 0th point, and on the right hand side that will be equal to the 0th y value. So I'll get back this equation I've got at the top. So that's that in matrix notation. I'm going to go to the board in a second and go through these again sort of slowly for a polynomial. So now what we did before was to get our squared distance and the error. So we rearrange our previous expression in terms of the error. So how far each measured point differs from our model. So the error is the particular measured point minus, again I've got a mistake in this upper subscript that I copy pasted. Yeah, so this is what I've just talked about, but rearranged to make the error, the difference between those two terms, the subject. I'm going to square it, and I'm going to add them up for each data point. This thing here inside the curly brackets is just the error vector. So it's the column vector with each of the errors at each point in it. So this squared thing is the sum of these squared errors at each point, and in the same way I've just explained it, that means it's the length of this error vector. It's the transpose of the error vector, all written out, replacing my previous expression, the vector version of it. It's y minus z, which is this matrix containing the basis functions evaluated at each of the different points. The transpose of that times that. And what we want to do in a certain sense is take the derivative with respect to our parameters and find the value of that which minimizes this expression. I'm going to go through that in a second, what this actually means. But it's doing the same process in actuality that we did before, which is taking each of the derivatives with respect to the parameters, setting them equal to 0, and seeing what comes out. And what comes out is this. The transpose of this matrix that contains the basis functions at each of the points times this Z matrix. So, because you transpose in that, it will be a square matrix, size m by m, the number of basis functions by the number of basis functions, and it will multiply our vector of parameters. And on the other side, we have this Z transpose, so transpose of that matrix times the matrix of values. And this is exactly equivalent to the set of simultaneous equations for the parameters that we found previously. And if we look at this set of equations, you can see it's of the general form: a matrix times something that we want to find equals some vector on the right hand side. So our A matrix in this sense is this Z transpose Z. Our X, our unknowns, are these parameters that we're optimizing in the problem. And then the right hand side, we get this matrix from the transpose of our matrix of basis functions and the Y values. So perhaps I'll get a whiteboard up and I'll try and write this out for a linear regression problem. Let's just see what it looks like and see that it looks the same as we had before. Let's see if we get this working. Yeah, it's not gone to sleep. I'm afraid there's a bit of reflection here, but we'll just have to live with it. Hope you'll be able to see this. So what am I doing? Let's see what this Z matrix actually is. So can I get this to sneak in on the side? No, not that. That's what I want to do. You can see that formulae sticking out. I hope what we've got is that Z matrix is equal to, I'm hiding, see my, I don't know if you can still hear me from here. Let's get the, I hope you can still pick me up on the sound. Okay, fine. We've got this. So if we take our linear regression model, we've got the y I equals a0 times I x value plus a1. This one's the 0th power, and this one's the first. So in this matrix here, in general, I've got, if I wrote my general formulae that I had there, I had a0, z0 evaluated at my position plus a1, z1 evaluated at my position. So now this is my first z, and this is my first basis function is 1, my second basis function is just the value of the itself. So here I want to have, if I look on the side of the screen, it's going to be z0 here evaluated at the so the value of x0 to the power 0, 1, and then in the next column, of course, I get z1 0, and that's going to be 1. That's going to be z. Now, obviously, my transpose is going to be 1. Everything might be a bit warm. It's not a very large blackboard. White. I'm going to remove those. But what happens when I? It's not a good place to put it. When I do Z transpose Z, it's going to be equal to. It's not a very good example in a sense because they're both square matrices. So Z transpose, I get 1 times 1 plus 1 times 1. So in these yellow now, I'm going to get sum over all my values of 1, or indeed x 0 to 0, xi to 0 times x. And then when I go to the next thing, I'm going to go 1 on this side, I'm going to get the first basic function to 0, and then on this side, going down this second column, yeah, 1, 0, in this case it comes to sum of 1, add up my n, actually 1 squared, if you want to do that. Sum of the x, and sum of the x, and then sum of the xi squared. So that comes out to be exactly the same expression that we had, that you would get by taking the derivatives with respect to a0 and with respect to a1. So those are going to be multiplied by a0 and a1, and on the right hand side we'll have this matrix times y0. When we multiply this out, I'm going to get that bit equal to, it's the right way to the sum of the y's and the sum of the x's. That's kind of what it looks like for the quadratic, sorry, for the linear thing. For the quadratic, it will be more or less the same, but then you'd have an extra column containing the extra basis functions. And if you had more than 2 data points, then the Z matrix will be rectangular and will go down, and the T matrix will be rectangular and long. So that's what this thing looks like. So to actually implement it, you just need to build this Z matrix by writing some routines to evaluate the basis functions at the different points, and then take these combinations of them. Well, you just set up that matrix, essentially evaluating all the basis functions at the different values, and then you can use our matrix multiplication knowledge, eigen your own thing, or NumPy to create Z transform Z, Z transform times Y, and then you use Gauss elimination or any other solver that you want to solve for the parameters. So here's another example using a slightly different set of basis functions, just to show that they can be whatever you like, as long as they are defined functions only of the independent variable, and they're multiplied by, in a linear way, by a parameter. So say we've got a load of data points. Here they are. And here they are plotted on a graph. You can see there's quite a lot of noise maybe here, or there's a much more complicated model that we don't know about. But let's say that this looks like an exponential decay with some noise on it. So let's try fitting it to a function with to a model with three basis functions. First basis function is 1, but its parameter a0. Its second basis function is e to the minus x, and that's multiplied by its parameter, and e to the minus 2x. So let's build our Z matrix. So going back to what I had on the board before, the top entry is the zeroth, the first, starting from 0. So the basis function labelled 0 evaluated at the first point. Again, our first basis function is a 1, so that's 1. Our second basis function is e to the minus x evaluated at our first x value. And our first x value was minus 3, so that should be e to the minus 3. So if you do exponential of 3, that should be what you get. And then e to the 6, so e to the minus 2 times minus 3. Then we evaluate these same functions at the second point, which is minus 2.3. And then so 1 evaluated at that point, e to the minus x, e to the minus 2x. And then we go down for all the data points. So if you see, we've got 11 data points, and we've got a column with a matrix with 11 rows corresponding to the different points, and 3 columns corresponding to the different basis vectors. Now I can form Z transpose Z. Again, if you're using eigen or numpy, it's just a question of using the times operator in eigen or the dot operator. But you've got to remember to take the transpose of the matrix when you're doing the multiplication. Both of them have got, in numpy there's a dot t, and eigen has got a transpose function. So you don't need to explicitly build both of them a bit together. You can build the Z matrix and then tell them how to transpose it. If you're doing it yourself, then you'll have to flip around your indices and make a separate copy. It'll be clever when you're doing it. So that's the Z transpose here. I've messed up in the slide. But once you do the Z transpose Y, you get a matrix with a vector with 3 values. And then you solve the linear problem to get these A values. And these, again, if we go back to our original model, are the parameters that appear in our model here, here, here. So our model for the data is this. So a constant intercept of about 2, because you see the data appears to be tailing off to some sort of plateau round about there. And then some amount of decay with this slower rate of decay, and a tiny amount of this. So it's not necessarily a particularly great model, but it fits. And you can see in a mean squared sense, the distance between these things is minimized. If we brought it up, we'd get a better fit to these points, but a worse fit to these ones here. I won't go into the details of this here, but you can think if there was noise in the system, we would expect the data points, the measured ones, if there was random noise, to be sort of distributed either side of the fitted line if our model was good, and you might expect that the distance from there will be distributed in some way. And as ever with stats, if there were enough data points and you looked at them from many systems, you might expect it to have a normal distribution. And it turns out if you chug through a bit of extra maths, which I'm not going to do today, the focus today was on sort of seeing how to get those parameter values in a systematic way. So I skipped over the derivation of where of how you go from this length of the error vector to this optimizing it. It's essentially taking the derivatives. I may have a go at doing that on the board in a second. Then I can always, you can always head off, or I can always cut it out if I make a big zero of it. But the focus today was just on trying to explain what the elements are in that Z matrix and how to set it up. But it turns out that this matrix on the left-hand side, this Z transpose Z, actually gives us a lot of information about how reliable our fit is. And particularly you can get errors on a particular variable, so that the variance in these parameters is given by the standard error, which is a measure of the total distance. It's essentially the square root of this thing we were minimizing this error, but divided by the number of data points, more or less. There's a little bit of so-called degrees of freedom, that stuff in there. For large numbers of data points, it's effectively divided by the square root of the number of points. And so the error comes from this inverse of this matrix at the appropriate, the diagonal element of the inverse of that matrix at the appropriate value for the given parameter. There's lots of stuff in the literature about where this comes from. If people are interested, we can dive into where that comes from. But for now, this is just a formula that you can work through that can give you error bars on your parameters in the fit. And then indeed, once you've got these error bars, you can do stuff that you may have come across at A level or in first year statistics, where you can do a confidence interval around the predicted parameters, and you can say whether or not they could lie within these different things that you can dig out. We won't really be using it, but just more in this context, just to make you aware that we've done it just in terms of minimizing this square thing, but you can think about a distribution of the errors and the parameters, and in various ways you can actually come out with some more robust sort of discussion about how good your fit is and what these parameters are likely to lie, which values they're likely to lie with. So if you wanted to practice doing this stuff, there is an example in the assessments tab where you're fitting a trigonometric function. So you're fitting a curve to a set of cosine functions that wibble faster and faster. You've got quadratic cubic problems that you've already had a go at, and I'll get answers back to the previous assessment as soon as possible, as normal. But there's also a linear regression problem that you can have a little go at checking up on how it works. you can go back and work through that exponential decay worked example that I've put there. Of course, you can find almost limitless problems on Tinterweb for you to have a practice at. I think it'll be very good sort of pulling together everything we've done so far. You can practice getting the data points, getting them in as vectors in whichever way. In the assessment on Blackboard, in the assessments tab, I've tried to provide it and stuff in a format that you can more or less cut and paste directly without having to do individual values. And here, same here, you can cut and paste this in. It should more or less go in. A bit later on, I think we'll take a little bit of a break from numerical stuff. We can talk about how to actually import spreadsheets. Import data from spreadsheets in a systematic way. Now, there's one more thing I wanted to mention, and this you will need for the assessment. So you see at the end, we've got our model for the system. So we found our best parameters in a least squared sense. And then this means that our predicted model, our prediction at any point, is going to be given by this plus this times E at the point we want to know. So if I want to find it at a point that's not on the graph, so say 0.5, but we haven't got an actual data point, the model, which is this green line, would put it at 2.13 plus that times e to the minus 0.5 plus that times e to the minus 1. And that would be our interpolated, our predicted value at that intermediate value. So that's one advantage of having this model. It provides us with some sort of insight into what functions are contributing to it. But it also allows us to estimate the model. If we do the estimation inside the bounds, inside the range where we've actually had information for the fitting, it should be fairly reliable. Of course, we don't know really what the function does out there, so extrapolating from this would be quite dangerous. But that's to say, so if we wanted to find it at a value that wasn't specified before, we do the fitting, we extract our model for the system, and then we plug in our value into the model to get the value that we're interested in there. So again, if you're going to use this recipe, essentially it is at the moment, we set up the Z matrix, we calculate the transpose of the Z matrix. You can write an extra couple of loops and swap indices and stuff, but both of the libraries I'm recommending, NumPy and Eigen, just have transpose functions. If you Google transpose NumPy or transpose Eigen, I'll show you how to do it. Provide examples later on, and I'll perhaps in Friday's class work through exactly a worked example of this. So find the transpose, then you multiply those transpose and non-transpose together, and you multiply the transpose matrix with the vector of observed values, and then you solve the system of equations. So as I say, I've given a recipe today, quite slowly I appreciate, but I think it's quite hard to see what those things are until you've worked through them, so hopefully it was clear and useful. Do read extra stuff. I've put links to here, but also I put a link into a more detailed derivation of where the formula came from. There's lots of stuff in numerical methods, numerical recipes, sorry, which is free, but you do need to, I would suggest having a private tab in a completely separate browser, and you need to enable Flash to get access to that. Capra and Canal, but almost all the books that are listed in the reading list will have a section on that. Well, any one of them or several of them probably explain it in the way that you like. So that's the talking at you bit for today. I'll stop here. If there's any questions, now's a good time to ask them. But you can also email Chris or myself at any point, and we will get back. Again, to emphasise, there is a new assessment on Blackboard, but the previous one should be in at 3 o'clock this afternoon. So thank you for listening. I hope that was useful. I hope it kind of makes sense. If people want me to go for any more or anything like that, just let me know. I'm happy